talking about membrane osmometry. And in one of the scenarios that we're going to talk about today, and actually often when you're working with membrane osmometry, I don't know what this guy is, but let's fight through it. We are going to be working with dilute polymer solvent solutions. And that's pretty apparent from essentially this diagram right here, where you have, again, very, very few polymers. The number of solvents, so again, in our previous notation, let's go back here, our solvent molecules drastically outweigh. We're looking at very, very dilute solutions here. So that is going to allow us to kind of do a couple of things. So if we are working with dilute polymer solvent solutions, we know that the number of moles of one, so again, species one is my solvent, much, much greater than N2. And that's going to allow us to kind of write out and do some simplification. So we look back on my volume fraction. If this relationship holds, this term is going to get killed. And we know that if I have x of 1 is my solvent, I know that the degree of polymerization of my solvent is just 1. So my volume fraction of my polymer reduces to this. And we know if this relationship holds again, my phi2 is going to be less than phi1. So, and we know that we have this relationship phi1 is equal to 1 minus phi2. If we have this relationship and we know that phi2 is going to be small in this dilute solution case, we can do this expansion of phi sub 1. So plugging that in, so why am I plugging that in? We'll see in just a second, is going to be equal to minus phi2 minus phi2 squared. Why is Professor Stein doing this? Well, if you remember all the way back to lecture 4, we had this expression for the change in chemical potential for our solvent. So we can now, if we're working in this dilute expression or this dilute polymer solvent solution case, which again, we had this expression previously for our general fluorohydrons of mixing. We had basically those two expressions, right? Hopefully people remember all the way back. And actually, let's go back and look at it ourselves, convince ourselves. So we had free energy equations looking at the chemical potential of basically here, the chemical potential of our mixed state versus the unmixed state for polymers and solvents. So let's go ahead and look back. Let's look forward. Let's go to look at our equation. So if we know that, again, that this expression, that phi1 is equal to 1 minus phi2, and phi2 is small, we had that expansion of phi1 being small. So we had that is equal to minus phi2 minus phi2 squared over 2. Plugging that in to this expression right here, we could then get this expression, which is a very, very, very important expression. We're going to expand on that in just a little bit. Also, remember that we previously described for an ideal solution that our chemical potential will be proportional to the log of activity. Again, this was in lecture 4, which is also going to be proportional to the mole fraction of that species in solution. So this is from Henry's law. So hopefully you remember this from Chem 24. And we've invoked Henry's law a couple times, but this was, again, talked about in lecture 4. We could probably find that in just a second. Should probably way back here. Excuse me. That's not so many derivations in lecture 4. So fruitful. Henry's law. You can look at it as that activity, excuse me. Here we go. This is effectively that Henry's law. Anyways, so I hope you remember back from that. So you could rewrite this activity, which is again a function of that mole fraction. Again, using that small approximation, you could get this expression right here, which is going to be equal to this phi2 over x2. So again, just a way to rederive and obtain this expression right here. So that is essentially exactly. So that's how we get this expression and this component of it right here. So that is from this kind of Henry's law expression. So you can plug that in and again, just convince yourself of that. So mole fraction again of the species solution. So let's look at these terms. So I'm really interested in this half of the expression because I have a couple cool things here. I have chi, so I could relate my change in my chemical potential of mixing, for my species, my solvent in the unmixed state and in the mixed state when I add that polymer solution. I have this chi parameter now. So in this term, there's these two kind of terms. So the chi term So the first term here matches with our ideal solution here. So this is my first term here. So if I just look at this expression for that chemical potential, this matches exactly my ideal solution model and what it should say. But my second term is really interesting because it has this chi and phi2. And these are two distinct kind of components here. This is also sometimes referred to as the excess chemical potential because it's this additive term. So it's the additional chemical potential considering my contact interactions or my solvent quality. Because again, we know that chi12 tells us something about our E12 interactions, and so that is going to also tell us something about our solvent quality. Or those, again, these interactions between monomer 1 and monomer 2. The other thing, this basically volume fraction squared tells us about chain connectivity and excluded volume effects. So think back, again, all the way back to lecture 3, where we had essentially those, actually, let's look back here. Let me see if we can find it quickly. So lecture 3, way down here, we had these excluded volume effects, and we said, basically as a function of this n squared. So actually, it's n cubed here. So this concentration squared term. So again, that's where we're kind of getting these contact interactions. So when we had those monomers interacting with one another. So we have in this excess chemical potential, this term right here that deviates from the ideal solution. So the ideal solution says that our change in chemical potential should just be this first term right here. But we have this excess chemical potential because we are not basically in this ideal solution model. We have some interactions between solvent and polymer that are going on here. So this is a really, really, really kind of critical term here because there's some really interesting things that could happen. Specifically, what happens to this excess chemical potential when chi is equal to 1/2? It disappears, right? At chi equals 1/2, there's a balance between our contact interactions and our chain connectivity. Or you can kind of think of it as our solvent quality and our excluded volume effects. So when that happens, when chi is equal to 1/2 here, we obtain our ideal solution model. The chain is behaving completely ideally. So basically, we are at, when chi is equal to 1/2, we're equal to our theta condition. Our excluded volume is 0 in this case. So that's why, again, there's this balance of basically balance between the contact interaction and the chain connectivity, or our solvent quality and our excluded volume effects. We know what happens when our solvent quality, if alpha is equal to 1, we know that our chain is exactly that same size as the chain in your theta conditions. And if there's, this competition or this balance between solvent quality and excluded volume effects, they both equally cancel each other out. We're in our theta conditions here. So when chi is equal to 1/2, we're in our theta conditions. And this shows you something really, really interesting, that we can change experimentally, because chi is going to be a certain value for any interaction 1, 2. Chi will have some value at a given temperature for any interaction 1, 2 that you're measuring. But we can change the value of chi because we know that chi is inversely proportional to temperature. So we could increase or decrease temperature to change chi in order to get into to make our chain, or to allow our chain, or to force our chain to behave ideally. So we could change this value to basically using temperature. So this is a really, really, really kind of interesting and cool finding. And one thing that I want you to know is that obviously this prefactor KT can easily be replaced by RT. And also the variables N1 and N2 are the number of moles, so not the number of molecules. So again, this is just for when you switch from KT to RT, that's what's kind of occurring here. It's just a unit. So obviously R is going to be your ideal gas constant, so 4 joules per K, whereas our Boltzmann constant was 1.38 10 23 joules per K. So that's all that's happening here. So remember, this expression is only valid in the limit of our dilute solution case. So phi2 much less than 1, and you could get this expression. So if we know, and we kind of derived previously, that the difference in chemical potential in our basically state 1 for our solvent minus that initial state is just going to be our osmotic pressure times the molar volume of our solvent. We have this expression here. We just derived this expression with, again, our ideal solution, our excess chemical potential here, and now we could just substitute it in, and we get this expression, which we are going to analyze much more. And actually, let's make some simplifications right now. So if we're in the limit of very dilute solution, so again, what we've talked about previously, what we've derived previously, we can approximate the total volume of our solution as the volume of our solvent. So the total volume of our system, V, so the polymer plus solvent, is effectively this right here. So this leads, again, if we're looking at molar volume, so like we've talked about previously, our molar volume is approximately equal to V1. So what's the physical meaning? The increase in the volume of our solution due to the addition of solvent molecules is approximately the same as the volume of a single mole of solvent molecules. So when we substitute this in to our expression, this expression here, that our molar volume, so V is equal to N1 V1, and basically our molar volume V1 is essentially equal to V1 right here. Again, this just comes from, let's go back all the way over here to our molar volume. So the change in volume due to this, due to the change in the number of moles, so that is our molar volume. So V1 is equal to N1 right here. So when we substitute this in, basically this expression right here, or effectively that V is equal to our molar volume right here, we get this expression finally. So now we can plug in, actually, let's go back here. So let's use, our volume is equal to V1. So, excuse me, our volume equals N1, V1 molar volume. So once we plug in here, we get this kind of critical expression. So we are going to look at this next time, and we're going to expand upon it just a little bit more. So thanks, and let me know if you have any questions. I will see you all next time. All right, have a good day. Bye.